Now we come to our next topic, which is integral and integral differential equations. So the general form for, so let's begin with integral equations. Integral equations. So the general form that we will consider is something like yt. So yt is our unknown function. Yt is equal to ft plus integral 0 to t k u t yu du. So here ft and the function k u t are known functions. So the problem is to solve for y. Solve for the unknown function yt. So we will focus our attention to the following type, which is called the integral equation of convolution type, which is especially amenable to the Laplace transform technique, and this is given by an integral equation where kut is a function small k of t minus u. So it only depends on t minus u. So in this case we have a convolution. So yt is the equation, integral equation can be written as y star k at t. So this kind of equation can be transformed quite easily. So we will take the transformed equation, taking Laplace transform on both sides. Transform on both sides. So you will get ys equals fs plus ys multiplied by ks, where fs is the Laplace transform for the known function ft and ks is the Laplace transform for the function kt. So ys can be solved as fs by 1 minus ks. So now the problem is to try to invert this kind of function to find the solution for yt. So let's take an example. So the example we can consider is where ft is e to the power minus t and the function kt is sine t. So the integral equation is yt equals e to the power minus t plus integral 0 to t sine of t minus u yu du. So from our formula for the transformed equation we get fs over 1 minus ks. The Laplace transform of e to the power minus t is 1 over s plus 1 and the Laplace transform of sine t is 1 over s square plus 1. So you get s square plus 1 over s square times s plus 1. So we can simplify this a little bit further. You can write s square over s square times s plus 1 and the second term 1 over s square times s plus 1. So the first term is simply 1 over s plus 1 and the second term is 1 over s square times s plus 1. So we can use partial fractions quite easily. So you will have a1 over s plus a2 over s square plus b over s plus 1. So if we solve this, we will get a1 to be minus 1, a2 to be 1 and b to be also 1. So therefore in the end we will get 2 over s plus 1 plus 1 over s square minus 1 over s. So we can easily invert this formula to get 2 times e to the power minus t plus t minus 1. So this is our solution. Now let's look at another example. This is given by the integral equation 0 to t minus u to the power alpha minus 1 yu du is equal to t to the power n. So this is a little bit different from our previous form, because there is no yu on the right hand side, but still this is an integral equation that we can solve. So take the transformed equation. So here alpha is a number between 0 and 1. So if you take the transformed equation, this is a convolution of t to the power alpha minus 1 and y. So you will get the Laplace transform of t to the power alpha minus 1 is simply gamma alpha over s to the power alpha. So you, on the left hand side, you will get gamma alpha over s to the power alpha ys. This is equal to t to the power n. Here I forgot to mention that n is greater than or equal to 1 is a positive integer, and so we get a very simple, on the right hand side you will have n factorial over s to the power n plus 1. So you get a very simple formula for ys, which is n factorial over gamma alpha multiplied by 1 over s to the power n minus alpha plus 1. So you can invert it quite easily, gamma alpha, and then the inverse Laplace transform for this is 1 over gamma n minus alpha plus 1 multiplied by t to the power n minus alpha. So now you can, if you wish, this is the solution, but you can also simplify it further using some easy properties of the gamma function. So properties of the gamma function that we will use is, first one is gamma 1 plus alpha is alpha gamma alpha, and the second is gamma alpha gamma 1 minus alpha is equal to pi over sine pi alpha. So this is called Euler's reflection identity for the gamma function. So if we use this, we have yt equals n factorial over gamma alpha times gamma n minus alpha plus 1 multiplied by t to the power n minus alpha. So then our denominator can be simplified a little bit, because gamma n plus 1 minus alpha, this is equal to, we will repeatedly use the first property. So I will write this as n minus alpha times gamma n minus alpha, and this is n minus alpha n minus 1 minus alpha gamma n minus 1 n minus 1 minus alpha, and so on. And so we will stop when n minus 1 equals 1. So you will get n minus alpha n minus 1 minus alpha up to n. So this term we want to be 1. So if we let n minus 1 minus alpha, then you get gamma of 1 minus alpha. So this is a falling factorial minus alpha 1 minus alpha, and then you have gamma 1 minus alpha. So yt is n factorial over the following factorial n minus alpha, n minus 1 minus alpha up to 1 minus alpha, and then you have gamma alpha times gamma 1 minus alpha, which gives you pi over sine pi alpha, and then you have t to the power n minus alpha. So this is your coefficient for t to the power n minus alpha for the solution. Now, as an application to physics, we will consider the so-called tautochrone problem. So this problem was first proposed by the Dutch mathematician or Dutch physicist named Christian Huygens. So this was proposed with regarding the construction of clocks, of pendulum clocks. And Huygens showed that the problem for a curve in the plane R2, so if you have a curve passing through 0, 0, let's say like this. So this is a curve in R2, and the problem that Huygens proposed was to take any point in this curve and consider the action of gravity bearing down. Force of gravity is in the downward directions. So if you remove a bead, so this is a bead, and if you remove it, it will slide down this wire. So, and it will reach this point at some taking some time depending on the height. So let's call the height as y. So let's call this point xy. So the height is simply y, and it will take time taken to slide down to the point 0, 0 is denoted ty. So the problem, Huygens problem or the tautochrone problem, is to find the curve such that ty equals ty prime for any pair of points y not equal to y prime. So this means that whether you remove your whether you let go of your bead from height y, or whether you let it go from height y prime, it will arrive at the same time. If they are released simultaneously, they will arrive at the same time at the origin. So this is the tautochrone problem. So tautochrone is made up of two words, tautos, which is same, in Greek, and chronos, which is time. So in Greek language it means same time problem. So this is the problem that Huygens proposed, and he also solved it, and he showed that the particular shape of the curve that solves this equation is the cycloid. So the solution was given by the inverted cycloid, in fact inverted cycloid curve. So we will see what the equation of this curve is, and we will consider Abel's solution to the Tautocone problem. So the problem itself can be transformed into a differential equation. So for this, let sigma y denote the arc length function with respect to y, meaning that at height y, the length of the function, length of the curve at height y is sigma y. So here we consider 2 points on the curve. The green curve is our wire, and P is the point where the bead is released. This is the point x0, y0, and the bead is released from this point. And we consider what happens at an arbitrary point Q given by x, y coordinates. So we have that the kinetic energy, so this is, we will use the conservation of law of conservation of energy. So we will use the law of conservation of energy which says that the potential energy plus kinetic energy at Q, potential energy at Q is equal to potential energy at P. There is no kinetic energy at P because the bead is released from rest position. So if we write the formulas for potential energy, this is simply mgy, and the kinetic energy at Q is half m. So m is the mass, mass of the bead is m, and g is the gravitational constant, and the kinetic energy at Q is half m times d sigma by dt whole squared. So t is the time taken to travel from P to Q, and sigma here is the arc length. This is the arc length sigma y. So the kinetic energy at Q is half m, the velocity squared, which is d sigma over dt squared, and the potential energy at P is mg times y0. So we get the differential equation d sigma over dt whole squared is equal to 2g times y0 minus y. So this implies that d sigma over dt equals plus minus square root of 2g times y0 minus y, but we know that the arc length will decrease over time, because when you start from P and go down, the arc length gradually will decrease to 0. So it must have a negative sign. We must take a negative sign because the arc length decreases. Arc length decreases over time. So now we can rewrite this as dt equals minus d sigma over square root of 2g times y naught minus y. And so if we let t y naught denote the time taken by the bead at p equals x naught y naught to reach the origin 0 0, then integral 0 to t y naught dt equals y naught to 0, because we are starting with the height y naught and ending at height 0, minus d sigma over square root of 2g times y naught minus y, and this will give us the equation t y naught equals integral 0 to y naught d sigma over square root of 2g times y minus y naught. Now if we write sigma y as fy dy, so fy is simply d sigma over dy, then ty naught equals 0 to y naught fy over square root of 2g times y naught minus y dy. And the tautochrone problem, if you have the tautochrone problem, then ty naught is a constant value t naught, because it does not depend on the height y naught. So we will get the integral equation 0 to y naught fy dy over 2g y naught minus y square root is equal to t naught, and we have to solve for fy because we want to find the shape of the wire for which this happens. So now if we take the Laplace transform and the transformed equation for this integral equation, this will give us the Laplace transform. So notice that we want to take the Laplace transform with respect to the variable y naught. So y naught can vary because we can release the bead from any height, and so y naught can be variable and for each such y naught we will get such an equation. And so we can take the Laplace transform by considering y naught to be our t variable. So then we will get fs, and then we will have a square root 2g factor, and you will get the Laplace transform for 1 over square root of t, which is square root of pi over square root of s, and on the right hand side you will get t naught over s. So fs, so here of course fs is the Laplace transform of f, and so we will get square root 2g over pi t naught over square root of s, and again we can invert this to find fy to be square root of 2g over pi t naught 1 over root pi 1 over root y. So this is some constant, let me call it c naught. So this is c naught over square root of y. And so we have found that the derivative of d sigma over dy is some constant over square root of y. One can show that this is the differential equation that the cycloid curve satisfies, but we can solve it explicitly. So remember that d sigma over dy is the square root of 1 plus dx over dy whole square. So this implies that dx over dy is equal to c naught over square root y squared minus 1, and you have a square root again. So this is simply square root of c naught minus y over y. So we can integrate on both sides to get integral over dx equals integral square root of c naught minus y over y dy, and so plus some constant of integration. So x equals integral square root of c naught minus y over y dy plus some constant of integration. So if we substitute y naught equals c naught sine square theta, this implies dy equals 2 c naught sine theta cos theta, and one can immediately get the answer x equals c naught over 2 theta plus sine 2 theta plus constant of integration, and y is c naught sine square theta. So since the curve must pass through 0 0 is a point on the curve, this implies that c must be equal to 0. So we have these two equations, and this is the form for the parametric form for the cycloid equation. Parametric form of cycloid curve. So the curve is called cycloid because it looks something like this, inverted cycloid. And the curve is the locus of a point moving on a circle that rolls along the horizontal line, horizontal x-axis. So we find that the equation of the Tautochrone, the solution for the Tautochrone problem is given by the cycloid. Now let's look at integral differential equations. These are equations that contain both derivatives and integrals of the unknown function, that contain both derivatives and integrals of an unknown function yt, say. So for example, let me take the following equation: y prime t plus 5 times 0 to t cos 2 t minus u yu du equals to 10, with the initial condition y0 equals 2. So let's take the transformed equation. We get sys minus 2 plus 5 times, so this is the function cos 2t, so you get ys over s square plus 4, and then there is a s in the numerator as well, and on the right hand side you will get 10 over s. So if you take the terms together for ys, you will get 5s over s square plus 4 times ys equals 10 over s plus 2. So this is s times s square plus 4 plus 5s over s square plus 4 times ys equals 10 over s plus 2. And so now you can simplify a bit. This is then in the numerator it is s times s square plus 9, and in the denominator it's s square plus 4. This is ys, and then you get 10 over s plus 2. So ys equals 10 times s square plus 4 over s square times s square plus 9 plus 2 times s square plus 4 over s times s square plus 9. And now you can invert it term by term, because you will get the first term is 10 over s square plus 9, the second term is 40 over s square times s square plus 9, then you have 2s over s square plus 9, and then you have 8 over s times s square plus 9. And if you invert this, you will get the solution yt equals. So if you invert this equation, you get this solution. So as an exercise, check that this is the, check that you get this solution. So in this way we can also attack integral differential equations using the same method as we have done for ordinary differential equations and integral equations.